Okay, here's our friend. Remember this problem? We had so much fun with last time. Um, so I want to talk through this a little more because I definitely did drop you into the deep end of the pool a little bit with this stuff. Although I will say about that, there's something I sometimes talk to classes about, and I probably should talk to every class. I probably should make it a policy to talk to every class. And I know I was talking to maybe Olivia about this, like, how many of you heard of like fixed mindset versus growth mindset? A couple people, a few people? Okay. Yeah, there's this idea that like, there's this educational psychologist, Carol Dweck at Stanford, who had this whole like fixed versus growth mindsets theory that's become a very popular thing and to think about. And it's like, especially in math, most of us, you know, have a totally fixed mindset of like, oh, I'm a math person or I'm not a math person. Most people have that attitude, right? Of like, it's just, I'm either good at something or I'm not good at it. And especially with math, but on lots of things in life. And there's this, so that's the idea of the fixed mindset is you just like think that it's like there's talent or something and it's not about necessarily just about hard work, but it's about like, oh, either I'm good at something or bad at something. The growth mindset is much more like, oh, I can grow and gain skills over time and put in effort and effort pays off. And eventually I can get good at, you know, decent at something. Maybe I'm not gonna be the best in the world at it, but I can try to, you know, get decent at it. And the problem with having a fixed mindset, and a lot of us have fixed mindsets about lots of things. I'm sure I have a fixed mindset about very many things, and it's always, I'm trying to change it to a growth mindset, is that if you have a fixed mindset, every single time you're tested at all, like any sort of like a new problem's put in front of you in math or any sort of like thing where you have to try to rise to some occasion, if you don't rise to the occasion, if you don't succeed, then the whole thing becomes a referendum on whether you are good or bad, right? It's like if you have a fixed mindset about something and you don't do well, you try to do something you don't do well, then that just is proof that you're not good at that thing, right? Whereas if you have a growth mindset, your idea is like, oh, okay, well, I'm gonna try this and I might not get it at first, but I'll get there, I'll work on it. You know, it doesn't mean I'm a bad person or a dumb person or something. It just means like, okay, this is a new situation. I need to figure out how to handle it and I'll take some time. People who know about this, am I describing it? People have better ways of describing it. I don't know if feel free to jump in if you have other ways of saying this that you think are good. But so I think a lot of educators care a lot about trying to have students have a growth mindset because it's just, because I felt like so much tension in the room on Monday when people like didn't know how to do this problem. And I was like, oh my God, like, wow, like there's a lot of tension in here. And I think sometimes it's good to like throw yourself into something and just be like, okay, I don't know what I'm doing, but let's try and be creative. Let's see what the problem's asking. Let's see if what we're doing makes sense. Like, let's try some stuff. And I think if you have a growth mindset, you feel freer to do that. Whereas if you have a fixed mindset, it's like, oh, if I don't know how to do this, then I'm bad somehow, you know? So, but it's everyone's a work in progress. I'm not saying it's like just a switch you can flip. Oh, thanks, Professor King. I never thought about having a growth mindset. Now I'll do that from now on. I know it's not like that, right? It's not that easy. And but I'm just saying, like, I think there's a whole thing of like, just it also is something about having like being presented with a problem you don't know how to do, and instead of just thinking like, oh God, how do I do this problem? I'm gonna fail this class. Like, oh, I'm in college and we're gonna be given hard problems and we get to think about them and have fun with them. And eventually we'll get there. And when we have tests, it will be about stuff we know how to do or, you know, presumably could figure out how to do. I mean, I like to ask questions on tests sometimes that are a little bit like past, like push you a little bit past what you're just have thought about, but using the concepts that we've thought about, but pushing a little farther because you're supposed to, part of being like, you know, part of like mastering a subject or getting better at it is like, oh, I can be thrown into new situations, right? So, you know, I'm always going to resist like just the recipe. Like when you see this kind of problem, this is how you solve it. When you see this kind of problem, this is how you solve it. I'd much rather think about the sort of the mindsets and the sort of strategies, the more generalized problem solving skills, right? That's what we care about. Small liberal arts college, we care about communication, writing skills, and generalized problem solving. Those are like the two big things, right? Because you're going to come out of here and be the leaders of tomorrow. And and actually, no, I have heard like trustees and other people say like people who were like computer science majors here or something who like went off into the world and were working with all these and ended up being more like a management type person, but because they could communicate, but then they could actually talk to the engineers because they had technical training and like be able to like bridge that gap, and that made them effective at their jobs and stuff. So that's like, it really is a good goal, because like to be able to like both understand things on a technical level and communicate is like a really hard, I mean, it's, if you can do that, you're ahead of like 98% of people. So you'll be okay in the world. That's my hope. Okay, anyways, I'm just rambling now. So let's go back. So, okay. So, and also like here though, I did sort of throw you probably a little too far to the deep end, because I didn't even talk about even this like paragraph above the first question about slicing our solid so that density is constant on slices. But I even want to back up farther and just look at this triangle for a second. So let me, because I thought about a different question I could have asked before even starting to ask these density and mass questions. So example. Yes, so it's an example of what, like we're getting towards like density and mass. So I'm going to go over to A and then problem 3 on this handout also. 2B is actually on the homework. But even before I get to that, I want to think about this triangle. We said right here, right, which is height 1. This is at 1, that's at -1. This is at height 1. What if I wanted you to find the area of this triangle? Do you believe you could do that? Yeah, you probably could do that, right? What's the area? It's base-time, it's 1/2 base-times height, right? But what if I said I wanted you to find the area using like a Riemann sum integral idea? Okay, so what's the area? The area, let's just know what the area is to be able to, what's the area of this triangle? 1? Yeah, it's base 2, height 1, 1/2 times 2 times 1. Or I could cut this triangle and fit it into that to make a square. So area is 1. But what if I asked you, pretend we forgot the area formula. What if I asked you to find the area using horizontal slices? Meaning like we're going to break this up. Just like we found the area, just like most of our Riemann sums have been vertical slices. What if I actually said, let's kind of break this up into a bunch of these little rectangles like this, right? And I'm thinking of a million of these little rectangles covering the whole triangle, very thin. Can you do that? And well, the answer should be yes, but there's some work to be done. And then another thing I wanted to get into is that somehow in class on Monday, we were getting into the similar triangle stuff. Most groups, I think maybe one group did it the way I'm about to do it, but I think most of the groups were using similar triangles to figure out like this width. But there's another way, which might be helpful, which is you can think about the equations. Like these are both parts of lines, right? There's like a line going off this way and this way, right? And this is part of that line. This side of the triangle is part of that line. So, and then how can you find the equation of that line? You know, it's y-intercept. You probably can figure out its slope. So what's the equation of this line? Negative x plus 1, right? Yeah, it's negative x plus 1. Or 1 minus x, I guess you could write too. So that's that line. This line over here is what? Very similar. Just x plus 1, yeah? Slope 1. You can tell the slope's 1 because it goes over 1 up 1. You can tell the slope's minus 1 here because it goes down 1 over 1, right? So y equals x plus 1 is that line. Y equals 1 minus x is that line. And if you want to do this with horizontal slices, you would have height y. If I was at height y, this could be dy, and you want the width of this slice, right? If you want the width of this slice, well, you're going from this curve to this curve, right? But it's an x value you're looking for. So I want to know the distance from here to here. So one thing that's worth noting here is that when we have y in terms of x, we can also get x in terms of y pretty easily. So like here you could say x is 1 minus y. You just move the x's and y's around. And here x is y minus 1. Subtract the 1 on the other side. Is that right? So if I want to go from like, you know, this is an x and this is an x. And so if I want the difference, how do I find the difference? So what's the width of one of these rectangles? The width of the rectangle at height y. How do I find the width? In terms of if I know these equations. Width is a horizontal distance. So what can I do? Well, we had the conversation, so I know you know the answer. What do I do to find, if I know that this a point, like say it's at height 1/2. Let's say y equals 1/2. Then what point is this? What's the coordinates of this point? Someone tell me. It's 1/2, 1/2, right? Because if you plug in 1/2 in for y, then x is also 1/2. So that's the point. So the right point is 1/2, 1/2. And the left point is what? I know this is 1/2. What's the corresponding? So if I know y is 1/2 there, then what's x? Negative 1/2, right? Yeah. So you know those. And so what's the distance from the left point to the right point? So the horizontal distance. It's really that minus that, right? 1/2 minus negative 1/2. So that width is 1 when you're at height 1/2, because you just subtract the two x's, right? X coordinates to get the distance across them. If it was if y equals, let me just do another example because there's a lot of halves floating around there. If y was like let's do y is like a 1/7. What's the x over here if y is a 1/7? Six sevenths, right? So the right hand point is 6/7, 1/7, and the left hand point is 1/7 minus 1, negative 6/7. So the distance, the horizontal distance is, the distance just between these 2 points is 6/7 minus negative 6/7, which is 12/7, I guess, which is 1 5/7. Okay. I'm just saying, like, as another thing you can do is you can concretize your life a lot by plugging in numbers and checking things and seeing if they fit the formulas, right? So, okay. So in general, at height y, what are we going to do? Well, we're going to have the point, it's supposed to be height y. I use ht for height. We're going to have the right-hand endpoint. I mean, maybe I'm overkilling this a little bit because it's going to be clear what we're doing. It's 1 minus y comma y, and the left endpoint is y minus 1 comma y. Yeah. So what's the distance? How do we get the distance? Between those 2 points, which is the width. So the width distance equals the width of the rectangle at height y equals what? What am I going to do? Tell me what to write algebraically. Yeah.
Well, you subtract right endpoint, the x component.
So subtract. Wait, do I want to do y minus 1 minus, which way do I want to do it? This way? Right, this is the one that's on the right. So you're going to do the right minus the left to get the distance, right? And so what do we get? We get 1 minus y plus 1, which is 2 minus 2y, which should look familiar from class Monday. That was what we found was the width. So if you don't want to use the triangle stuff, you can actually use what Descartes' whole plan was, which was to the Cartesian plane. You can use like algebra and write down equations of lines and equations of surfaces and stuff and figure out, okay? So maybe I didn't even need to go through all this, but I'm just saying, like, if you just want the width, it's just like, you just use the equation here and the equation here, but you want the x coordinates, so you have to solve for x in terms of y, yeah? Too much belaboring? Probably too much, okay. So, but then that means what you're doing is then the rectangle at height y has area width times height, which in this case is 2 minus 2y times the height dy. We just think of it like really tiny thin. And there are rectangles, there are slices all the way from the bottom is at y equals 0 and the top's at y equals 1, right? So slices from y equals 0 to y equals 1. So the area is the integral from 0 to 1 of 2 minus 2y dy. And let's see if we actually get 1, as we're supposed to. I think that integrates nicely to just 2y minus y squared. Yeah. So, I thought I felt a wave of excitement go through the class. 2 minus 1 minus 0 minus 0. Hey, I think that's 1. All right. Woo. Okay. That's exciting. So you can find, and this will definitely come up with harder, like, you know, things that aren't triangles, but actually have curved sides. You could still find the area of this way, right? Also, you could do this using vertical slices, but then you have to notice that there's different equations here. The height of a, now the height is a y value. So the height of a rectangle over here would be given by x plus 1. The height of a rectangle over here would be given by 1 minus x. And so you would have to like do 2 separate integrals, right? So with, let's write that quickly with, maybe I'll, because that's more what we've done in the past. So, sorry, with vertical slices, just like, write this almost down immediately. It's the integral from -1 to 0 of x plus 1 dx plus the integral from 0 to 1 of 1 minus x dx. Right, because now you're just, the heights are different. I'm just using the equation on the left for the left part and the equation on the right. And you can check that this works. I mean, this should each work out to 1/2, I guess, because they're half of the triangle. Right? Okay. Now, I wanted to do this because I think, especially the horizontal slicing way, I think this will be helpful when we think about the density and mass stuff. And I just want to talk about this one more time, just about the concept behind it, and just to show you the integral that you end up getting out of it. So, yeah, now there's this question of like, oh, if the density was constant, then you could just find the mass, right? If the density of the triangle is constant, say delta is like, I don't know, 5 grams per square centimeter. Sometimes this is called like an area density because we think of density as being, we think of, density as being mass per unit volume. But since there's really not like a third dimension here, we just say mass per unit area. We just think this is like a thin sheet. Well, what could you do to find the mass? You could say the mass is just area times the density. But I want to notice you could multiply by the density afterwards. And just think about, I know the entire area and the density is constant, so I'm just going to multiply by the entire density. Or you could find the mass of each rectangle. Like just think about the horizontal rectangles. So you could find the mass of each rectangle and then integrate. It's sort of it ends up being sort of besides the point here because you'll get a 5 inside the integral, which you can pull outside the integral. You know what I'm saying? Like, so mass of a rectangle let's just do the horizontal slices. I just meant this was on the side. The mass of a rectangle, the rectangle at height y, would be the area times would be the density times the area, which is here 5 grams per centimeter squared times 2 minus 2y centimeters times dy centimeters, right? The units then work out, cancel, and you just get grams. So 5 times 2 minus 2y dy grams, and then integrate. Okay. To get the total mass. Right. The reason I'm saying that is because if you don't do that, you could just do it after the fact, but what if the density is not constant? That's really the thing, right? And one thing that's worth thinking is like, what if the density was actually a function of both x and y? So I didn't give an example like that here. And the reason I didn't give an example like that here is because you need multivariable calculus to solve it. But I do want to think about this. Like, say I have this triangle like this, right? And the density, say the density is like, I don't know, say the density is like delta of x comma y, and it's like x plus y plus 4 or something like that, right? So that would be harder than these situations. What would you have to do? How could you estimate the mass? This is a problem you can think about. How would you estimate the mass? Well, now you could think about breaking this up into a bunch of tiny little squares or something like that. This is actually what we do in multivariable calculus. You know, we've been writing these things as rectangles, but like we could break them down further as little squares. That's supposed to be a square. You could just imagine a grid of squares covering this thing, right? And then at each point, so for like this one, you could basically say that the density is constant because it's so small. On a tiny square. And then so how would I find the mass? How would I estimate the mass of this tiny square? Like, let's say this is at the, here, I can give you a specific point. Let's say the point, I don't know, 2/3, 1/3. Let's say that's the point 2/3, 1/3. How can I estimate the mass? And well, okay, then I need a width, right? So like width, maybe I'm not giving you enough information. And let's say this thing is like delta x by delta y is the size. Doing multivariable calculus. So I gave you a density function and I gave you a size. How do you find mass of the tiny little rectangle? Yeah.
Calculate the area by the size of the y and multiply by the area density of the.
Yeah, so but what is the density at this point? What's that?
Evaluating the function.
Yeah, right. So you're plugging this point in here and you're saying, oh, well, because I'm saying like, just treat the density, because this is supposed to be tiny. Let's just treat the density as constant on this thing. That's how you would estimate, right? And so if I plug in this point, I could say the density is approximately 2/3 plus 1/3 plus 4. I think 2/3 plus 1/3 is 1, right? So here delta is 5, right? At this point. It's a little unfortunate we're talking the same number over there. Let me change this to like +1 or something. Just because I used the number 5 over there, I don't want to be confusing. So here delta is 2 on this little square. If we're treating the density as constant, right? And so then the mass you're saying is that it's the same formula. It's area times density, right? It's density times area. Which in this case would be 2 grams per centimeter squared. I guess I should have given the units here. Times, and yeah, Finn was saying it's basically delta x times delta y, right? So that's how you would that's how you'd estimate, I guess, approximate mass is that. So you would have it for one little tiny square, you would have the mass, an estimate of the mass. And then what would you do? I have it for one tiny square. What would I do next? Give up? Rebecca? Sorry, Rebecca's. Yeah, so you would just do it for every, you would do the same thing for every little tiny square that you're using to cover this. And that would give you a mass of all the tiny squares, right? And then you would add them all up. Right. But that sounds like something a computer could do maybe. But you could write down a Riemann. We could write down like some sort of weird double Riemann sum. Again, this is beyond what we're doing in this class, but I just kind of want to give you the general sense of like what the problem would look like if the density function really was not constant. So I'm just gonna say, then do the same for every little square. Little square. And add. Okay. So that would be the problem. And then the question is, we wouldn't really know in this class how to turn that into like integrals because there's two variables that are changing. Turns out again, and when you get to 1800, you do like what's called a multiple, there's something called a double integral you can set up. I mean, you can sort of imagine this, that like for the same y value, if I did take just like a strip of these squares at the same height, that actually I could almost do some sort of integral in terms of x to like, if I could set it up right, to find the total mass of this rectangle. And then do another integral in terms of y to find the total mass of the whole triangle. You could do that. Luckily in this class, we don't do that, right? So, but I'm trying to give you a sense of why it's nice when we just have one variable. I think that's the thing that I didn't get across last time, is like, if we look at the example A, where the density function is just in terms of y, right? So, there's math back there. Okay, so this is what I'll say. So, if the density function is just in terms of y, then I guess the point is like at the same height, like at that height 1/3 up there, we could actually just do all of the little squares all the way across at the same height because the density is the same, right? If delta is a function of y only, as in delta 1 of y is, what was it, 3 minus y squared grams per centimeter squared. Then, right, then we can actually, then all the little squares at the same height give the same result. And so we might, instead of doing it across all the little squares at the same height, we might just well do the rectangle, the little rectangle at that height. Does that make sense? Then for a particular y, like y equals 1/3, we can find the mass of the whole rectangle, the whole sort of thin rectangle at height 1/3, or at height y. Since the density is constant, since the density is the same everywhere at that height. Okay, so and then it's still, so then it's still like mass equals density times area, right? Except we don't have to resort to little squares, we can do the whole rectangle. Density times area here. And the density is 3 minus y squared grams per centimeter squared. And what is the area? Well, we found the area already when we did the area integral. It was 2 minus 2y dy, right? So it's the same as before. I'm just saying, like, that's why I wanted to do the area problem first, because then it's sort of clear what we're doing. And then, so this is that's the mass of the rectangle at height y, of the thin horizontal rectangle at height y. Thin horizontal rectangle at height y. Okay, so the mass of that thing is density times area of the rectangle. And so that, when at the top of the handout where I say, find a way to slice our thing so that density is constant on slices. That's the idea here, right? Is making it constant on the slice lets you avoid having to do like a multiple integral, basically, having to do something that's beyond our capabilities at this point. If that makes sense. So, right, so we find this nice way to slice it so that the densities, so the function, I mean, this is going to apply to lots of situations where the function we're measuring is constant on the slices, so that we can actually find an integral that we can do. And then, and then you integrate kind of perpendicularly, right? Because you're really, the y is the variable here. So you're integrating, the slices are this way and you're integrating this way. So then, just to wrap this up, just to say it like, then integrate, then the total mass is the integral of all the other masses, right? And total mass is the integral of all the masses of the thin horizontal rectangles. And the bottommost rectangle is at 0. The topmost rectangle is at 1. And this is the function that you're integrating, right? So that's why we ended up with that formula. Okay. Now, one reason I'm going so deep, like carefully with this, is that on the homework is part B, because it was a problem I picked from the book, so I assigned that problem. So you want to do the same idea, except there's going to be 2 integrals again because the function is changing, right? But you shouldn't necessarily know how to set that up now. Does that make sense? Questions about any of this? Good. You see how things go from impossible to boring really quickly in math? That's the problem with math, actually, is that like, it's I guess it's a fixed mindset thing, but you feel stupid when you can't do something. And then when you can finally do it, you're like, you feel stupid for not having been able to do it. So you never get, you feel smart for like the 2 seconds that you figure something out. On both sides, you feel stupid. So that's great. That's great. Why do I do this for a living? All right, so okay, so that's the mass. Okay, so let's look at problem 3. That's the one I want to look at just quickly, because it's a little different. Because now I want to figure out what the slices of this thing should be. So this is, so the problem says, I'll share screen just for briefly. So the problem says, right, there's some sort of oil spill, and as you get farther away from the center, so when R is 0, it's 50 kilograms per square meter, which seems like a lot. But as R grows, it's going to get like thinner and thinner, right? The amount of oil is going to be less as you go away. course, it probably doesn't work like this where it spreads out in this precise way, but you know, idealize the situation. So, okay, so this is a density, but now this is distance from the center of the oil slick, right? And so let's try to do this problem. Start down here. So this is problem 3 where the oil slick radius 1,000 meters. The density is a function of R, which is the distance. So that's kilograms per square meter. Oh, square meter, per meter squared, yeah. Okay, so 50 kilograms per square meter. So our oil slick looks something like this, right? It looks something like a circle. And this is 1,000. And the question is, how do we slice it now? Because we want, like, where is the density constant? What kind of thing is the density constant on? Is it constant on vertical slices? R is the distance. I guess distance from the origin here, from the center, from the origin. So if I take points on this slice, does this point have the same density as that point? Yes or no? It all depends on the distance from the center. Are these the same distance from the center? No, right? So it changes on vertical slices. Same thing with horizontal slices, it changes. What does it not change on? Circles, right? You could put circles. So this is constant on circles. So if I had some circular, so now I want to break this up into a bunch of circular, like little wedges. Annuli, is annulus, is that the right word for it? Donut, really thin donuts. I don't know if you'd be excited getting this donut to eat, unless the radius was like a meter, like a really thin donut that's like, I wonder if you could make a donut like that, probably might be hard. Okay, so, right, so now, this is constant on circular. It's like not even really slices because you can't use a knife to slice it. Or I guess if you're careful, slice it around. But so bless you. So the density, bless you, is constant on circles, right? On these concentric circles. Okay, so this is just a nice little trick for this. It's like, so, I mean, of how to calculate this. So the density is constant on circles centered at the origin. So I need to find the area of one of these circles, right? So let me try to draw one of these again. Like, there's a circle. I'm going to draw a thinner circle inside. I mean, a smaller circle, just very, and so I'm supposed to think of this thing. This has width dr. I'm just going, I could say delta r, but I'm just, I don't know, I'm skipping the Riemann sum step and going straight to the integral, right? So width is dr and the radius is r. And I would like to approximate the area of this thing. So I mean, you could do something like the area of the whole circle minus the area of the smaller circle, but dr is supposed to be super duper tiny. So there's a trick here, which is snip and unroll. If I cut it and then unroll, I can make this basically into a long, thin rectangle of height dr. And what's the length? What's the width of this rectangle? Circumference, right? So the width is so it's dr by the circumference. Which is what? Let's remember your circumference formula. 2 pi r. So that's 2 pi r. And so it's 2 pi r dr. By the way, so this is how pi was originally defined as the ratio of a circumference to the diameter of a circle. One thing we could do is think about what we did with the triangle first. We actually found the area of the triangle without doing this density function, weighting different parts of it. You could find the area of the circle doing the same thing. Note, the area of the circle is the integral, is the sum of the areas of all of these annuli. I think that's the word, annulus. Sum of the area of all these thin donuts, which really is the integral from 0 to like 1,000 of 2 pi r dr. I just want to think about what happens when you integrate 2 pi r. What do you get? You get pi r squared. It's no coincidence that the circumference is the derivative of the area. Have you ever noticed that before? If you differentiate pi r squared, you get 2 pi r. And if you integrate 2 pi r, you get pi r squared. So that actually really is where the area formula, I mean, that's the thing, like that's where the area formula comes from in some sense. Because the pi is all about a ratio of 2 lengths. So why does that have anything to do with area? It has to do with area because that's what you get. Isn't math cool? I saw a few heads exploding. There you go. So that's kind of cool. I'm just gonna do that. Probably super uncool to write the word cool exclamation point. But I just want to mention that. Okay, but really what we want to do now is we want to do the same thing we did before, which is we want to weight that area by the density function. We want to multiply it by the density function, right? So actually then the mass of a thin donut is the density times the area. This is why we did the slices this way, so that the density would be constant. The density is constant everywhere on this thin donut, right? That's the point. Because it only depends on the distance from the origin. And so that in this case, given by the problem, is 50 over 1 plus r kilograms per square meter times the area, which is 2 pi r meters times dr meters. And that's why you're gonna get kilograms, because the the meters are all gonna cancel, right? And so you get 100 pi r over 1 plus r dr. I think if I just multiply that out. And so the total mass is just the integral of that from 0 to 1,000, right? I'll take the time to do this integral, although this one is a little bit tricky. Could be a little tricky. There's the r on the top and the bottom. you could let u equal the bottom. Because then the top, I'll just say this, I mean, I'm not gonna go through the whole thing, but if there was a problem on a homework that was like this, where it was under a square root, like there's like a 2 plus z under a square root or something like that. Then r is actually u minus 1, and dr is du. So you can actually turn this into something much easier to do if you do that. Because having the plus sign in the denominator is sort of annoying, but. Okay. Okay, so you can work out what this is, but I don't, again, I care about the setup so much more than I care about the answer. Okay, how we doing? Any questions on any of that? It makes sense why we were taking these circles, and this was kind of just a trick to, if you unrolled it, it wouldn't be a perfect rectangle, but you're approximating. Let's take a break for a couple minutes. You guys need a break, don't you? All right, let's take a break for a few minutes, and then I want to talk about center of mass. But I think hopefully the density stuff seems much less intimidating than it did. I also always, I talk too much. Do I talk too much, guys? Yeah. No, I always think it's gonna take like half the time it actually takes. I was like, that'll be like the first half hour of class. That's like the first 55 minutes of class.
Question.
Yeah.
Yesterday's problem set.
Oh, yeah.
I think number 25 has two answers.
Which was 25?
25 was we had 4 sections. They ask about the height behind the slice. Yeah.
Oh, the H8
Yes.
and the R8 and all that stuff. Yeah.
Depends on what kind. It's like whether a left or right.
Yeah, that's right. That's right. So right, it could be 3.5 or 4, the height at the 8th height or something, depending on how you count.
Yes.
I agree. I should tell the graders this because I think the way the book wrote everything was like the sum from 1 to n. So it felt like it was always a right, like a quote unquote right sum. So that H1 would be 0. The first height would be actually 0.
So it's 7 delta H.
Yeah, I think that's kind of what it ends up being. That's right. But I'm going to tell the graders to watch out for that because.
It could be.
Yeah, it just depends on how you count everything, right? And so. But I checked the solution manual, and the solution manual says like 3.5. It says like 7 delta H for the first one. So, but I almost feel like I like the answer 8 delta H better because H0 should be the bottom, and H or H, however many slices, 20 slices should be the top, right? In which case, like that's how it should be counted. But I don't know. I just looked to see what the back of the books, like what the solution manual said. So, but I'll try to tell the graders to.
Did you go over 25?
Go over it. Like where the counting with the slices, the one we were just talking about. I can probably rather do it in office hours or like Friday when we're here hanging out. I mean, I know you'll be looking at the next problem set just because we only have like 25 minutes left and I want to talk about some of the center mass stuff before because I'm giving you, I think I put some homework on it for Friday, so I want to talk about it before. So I'm happy to talk to you anytime. Our phones. What is this math? I don't know.
Advanced integral is already out there. I don't know what that is.
Well, out of context, it's very hard to know, like, you know.
Like seeing calculus on the board as a freshman.
Yeah, right. What is this magic? Okay. Let's get back to it. So one thing I want to talk about here, I think it's better to start with the idea of just point masses and how you would like balance an object. Like if I had a rod and I was hanging some weights from it and I wanted to balance. Like say I have sort of like a steel rod, hang weights from it. Find the balance point. That would be the center. That's called the center of mass. That balance point. So if I take a rod and I hang like the same weight from either side, either end, where's the balance point? Not a trick question. Where's the balance point? In the middle, right? Okay, but what if now I put like I'm holding this rod and I put like 2 kilograms here and 1 kilogram here. Where's the balance point gonna be now? Can anybody tell me? Closer to the 2 kilograms? Can someone tell me exactly how far from each end it is? Let's think about it. I mean, there's even a question of like why it should balance at all. The one side's heavier. Shouldn't it just tip over no matter where you try to? I should have made this smaller. So if I hold it in the middle, what's going to happen? I tip that way, right? But I feel like this is kind of physics and it's kind of strange. It almost seems plausible that even if I held it like right here, that because this weight's heavier, it should still tip. But it doesn't. That's not what we experience, right? What do we experience? Can anybody guess how far along this is, the balance point? Three quarters, like one quarter from this side, 3/4. On the what?
On the other side?
Oh, you want me to be over here?
Oh, wait. Yes. I don't know.
Okay, that's the first question is, should it be farther to the left or farther to the right? Left is your experience is that it's left? Okay. So a quarter is not a bad guess. It's not the right guess. Can anybody? It's a third. Why is it a third? That's a question, right? So the balance point is a third of the way. The reason is because that means that like the ratio of these two is what? The ratio of these two distances. Somebody say it. 1 to 2, 2 to 1, 1 to 2, right? And that's the thing that balances actually. That's this notion of like torque. I think that like, yeah, it's also like a thing of like, if you try to hold a weight just like in your hand versus holding it at the end of a long rod and trying to lift it up, it's like much harder to lift because it's somehow the distance away from you horizontally also affects the lifting, you know? You ever tried that? I don't know. I guess I should have like props or something, but I'm a mathematician. We do everything in here. So, but yeah, so it turns out that this is kind of like, you know, it's this thing, it's more, instead of just the concept of just the weights, it's like the weight times the distance has to be balanced. It's not just that the weights are balanced, it's like weight times distance has to be balanced. Times distance. Wait a minute, I should actually use like a weight times distance from center must be balanced. So in fact, if we wanted to do this kind of like mathematically, we could say like, if this, I mean, to get to this 1/3, if we call this length maybe L1 and this length L2, then we would want 2 times L, like here, we would want 2 times L1 to equal 1 times L2, right? If that's what you're about, if that's what's actually needs to be equal. When I say balanced, I really just mean equal. In this case. And then that means L2 is twice L1. And then that tells you why it's 1/3 of the way, right? So that's the concept. What if we had like 3 masses now? Let's try it. Let's do an example. But here's where I'm going to start to coordinatize everything because life gets more complicated, and when life gets more complicated, we want to add coordinates. That's an old saying. Goes back to, no, I just sounds like it's supposed to be some general thing. So let me hang a, I don't know, 5 kilogram weight here. 4 kilogram weight here, and 7 kilogram weight. I don't know. Maybe it should be bigger. And let me decide on some stuff. Let's say this is let me make a I need to say how long this is. So let me make an x-axis here and say this is 0, this is 2, and this is 5 or something like that. You can do meters, centimeters, whatever you want to do. Okay. Now you could make a contraption like this and try to hang things from it and try to find the balance point, right? And you could just find it experimentally just by holding it and seeing if it's tipping to the left and then find some point where it's stabilized. But how would you do this mathematically? Well, where do we think it might be? Little like over here, sort of. Okay, so let's say this is the balance point right here. Center of mass. Let's actually call it X. Okay, then what's the what do we need to balance? So we need the weight times the distances to balance, right? So the weight times the distances on the left should equal the weight times the distances on the right. So then 5, how far is 5 from the center? far is that? 5 times x, right? It's the thing we don't know. So 5x plus 4 times, what's this distance? X minus 2 should equal 7. And what's this distance? What's that distance? This is x minus 2. What's this distance? 5 minus x. Good, equals 7 times 5 minus x. And now you can just solve for x, basically. Solve for x. So 9x minus 8 is 35 minus 7x. It's not necessarily going to be the nicest number. Oh no, okay. So that means 16x equals 43. So x is 43 over 16, which is 2 plus 11 over 16, I think, 32 over 16. So yeah, it's a little bit to the right of center. A little bit to the right of, not center, actually it's a little bit to the right of center, but it's a little bit to the right of the 4 kilogram. Actually, it's a little bit surprising because there's more weight on the left half than on the right half. So you might guess it's on the left half, but it's actually a little bit past the halfway point because 2.5 would be the halfway point. So it's not necessarily easy to figure this out, right? But does that at least make sense?
Can you explain like one more time where 5x comes from?
I guess it's the 5 times, it's this 5. Sorry, yeah, I picked 5 for both those numbers, which is bad. But it's 5 kilograms times x minus 0 is the distance from theirs to there. Yeah, sorry about that. Now there's a problem here though. What if I went to like 23 weights? Part of the issue here, part of what we did here was we sort of guessed about where it was. So we could get these signs correct, like that this is 5 minus x instead of x minus 5, right? But I want to note something. I could actually move this to the other side and flip this around and make it x minus 5 instead of 5 minus x, right? Because if I subtract it over, 5 minus x becomes x minus 5. So I could rewrite as 5 times x minus 0 plus 4 times x minus 2 plus 7 times x minus 5 equals 0. This will work actually, because if you subtract this over, you have a minus sign, but the minus sign will distribute through and flip the signs of these. And so it's actually kind of not, you can actually write it in this sort of, this is a more uniform way, right? There is a name, this is sometimes called like the moment, this weight times distance thing. You can think of it as like a torque, maybe, but it's also sometimes called the moment of the mass in this system. And so what this says is that this, i.e. the sum of the moments is 0. That's how you find the balance point. Okay, that's kind of the way we do this, is like the sum of the moments equals 0. And actually it's on screen too, the sum of the moments is 0. Like this, that when we go to integration, when we go to like continuously distributed masses, you have to do an integral, and it's like going to be kind of the same idea, which is like that whatever our function, what it's really like our density function times our distance from the center, right, is what's going to end up being the thing that we want. So, but you see, like this is kind of nice, and then you could just solve, you can still solve this and you get the same answer. Okay, so this is how it works for point masses. If you wanted something continuous, well, let's think about, I think the first thing I asked you to do was to think about the rod Yeah, there's all this formula stuff that's really kind of ugly, which we'll talk about. The center mass of the rod from problem 1. So this is an interesting thing, like where would I hold this rod to balance it? Right, if it was uniform density, you would just hold it in the middle. It's length 2 meters, you would just hold it at 1, right? X equals 1. You put your finger there and it would balance. But this one actually gets heavier as we go from left to right. And so I want to think about this in terms of, well, let's okay. If we go to things that are no longer, so for point masses, you just do that. You just add up all those and solve for X. Even if there were like 20 masses in some long thing, you could figure it out. May not be fun, but you could figure it out. So what about continuous masses, like a, so for example, this 2 meter long rod, where the density was, what was it, 2 plus 6x grams per meter. So now up there, I was actually thinking of the rod as sort of being massless. I was idealizing the situation and not considering the mass of the rod as part of the scenario, right? But I'm not hanging weights here. I'm just actually giving each piece of this weight. And so you could do a Riemann sum idea, which is you could break this up into pieces, right? I could like, well, here, let me put my x-axis on here again. That's 0, that's 2. If you wanted, I could break this up into like 10 pieces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? We could break this up into 10 pieces and approximate by just thinking of the math. Like we could find sort of, we could just choose a density. We could just plug in an X in this interval. If we wanted to estimate the mass of this little piece of the rod, we could plug in an X, get a density, pretend that's the density of the whole little piece. So multiply by its length would give us the mass of the little piece, right? So if we had like x1, x2, x3, just somewhere inside these, all the way up to x10, I guess. So we could estimate. So the mass, so we break up into n pieces, right? Then we would have the mass of the, and so we would have, and the length of each of these would be delta x, right? In which this case would be 0.2, I guess. So the mass of the ith piece would be the density times the width, right? And but this is where you sort of assume it's constant. Right, you're just assuming it's constant on the ith piece using just delta of x. So this is really delta of xi times delta x. That would be like the mass of each piece, right? And then if you wanted the moment, so the moment is mass times distance from the center. The center is unknown though. So we need to give the center, okay, here's a problem. I use the variable x up there. I think, but we're already using x. I think if you look at these formulas that you're given, they actually use x bar for the center because it's a specific number. So they actually use x bar. So maybe I should have been using x bars up here for everything, you know, probably would have been smarter. If I just called this x bar to begin with, it's like some specific x. you know, just go back and put bars over every X that you saw. Sorry. So, if the center of mass is X bar, then the moment, so we have the mass of the ith piece, it's this. Then the moment of the ith piece is its mass times the distance from the center of the mass, right? If that's true, then and let's just use the xi's again, then the distance from the ith piece to the center of mass is, well, it's really like xi minus x bar, or x bar minus xi maybe. It doesn't really matter because you get 0. It doesn't really matter whether I put x bar minus x or x minus x bar here, but just to maybe mimic that, maybe I'll say x bar minus xi. Right? And this will be negative for the xi's that are on the right side of x bar. This will be positive for the xi's that are on the left side of x bar. Right? So the moment of the ith piece is the mass of the ith piece. So delta of xi times delta x times the distance. It's like a lot of mumbo jumbo, but but I think I'm just trying to get at what, you could really do this with 10 pieces and like find and pick of the center of each piece as your xi's or whatever, and actually compute all these and estimate the center of mass this way. You got a 105, right? Okay, okay. So that's the moment of the ith piece. And then, so we want that we want to find x. This is unknown at this point, the x bar, right? This is unknown. This is what we want to find. Want to find. So we want the sum of the moments to be 0. Or we set the sum of the moments equal 0 to find x bar. Okay, so here that would be something like the sum I equals 1 to n of delta of xi. I'm going to rearrange this a little bit to put the delta x at the end. X bar minus xi times delta x equals 0. Okay. Again, if you were like wanted to do this for like 10 pieces, this would all be very doable. This would be unknown. I mean, it would be kind of like this, right? Like this would be some specific number by plugging into this function right here. Delta x would be a specific number. So the delta xi times delta x would be a specific number. The xi's would all be specific numbers. And you would get a formula that looks very much like that you would solve for x bar. Is that fair? Okay. So then, but really what we want to do is, this is an estimate. This is kind of a Riemann sum idea. And what we actually want to do is turn it into an integral. So as n goes to infinity, because we're getting, this is just always the Riemann sum idea. Only like 2 ideas in this course. There's only like 10 good ideas in the history of man. We just use as much as possible. So now this instead is the integral over the whole width. So that's the integral from 0 to 2 of delta of x, now the xi's go away, times x bar minus x dx equals 0. And let's just see if we can solve this, because we have a specific formula for delta of x. Just see if I can solve this in the last few minutes. Oh man, of course, I didn't push the board up. Okay, let's just see if we can solve this in the last few minutes. So because it's kind of weird. Because now instead of just computing an integral, you're trying to solve for some unknown. So let's think about the weirdness of that. So, okay, so the integral from 0 to 2, delta x is 2 plus 6x times x bar minus x dx equals 0. And I want to find x bar. Seems strange, right? Except here's what you do. I can multiply this times x bar and multiply this by x. I want to sort of isolate x bar somehow. So that the left-hand side, I could rewrite as 2 plus 6x times x bar minus 2 plus 6x times x dx equals 0. All right, I just multiply the 2 plus 6x by each of these. Now I can actually break it up into two separate integrals over the minus sign. So this is the integral from 0 to 2, 2 plus 6x x bar dx minus the integral from 0 to 2, 2 plus 6x times x dx equals 0. This is certainly something we can evaluate, right? I might go a little fast just because we're going to run out of time and I want to see how this works. But evaluate this. You get integral 0 to 2, 2x plus 6x squared dx. So that's x squared plus 2x cubed from 0 to 2. I think I made the numbers work out somewhat nicely. I think that works as an antiderivative. So I get 4 plus 16, which is 20. Okay, so I did that very quickly, but believe me that this equals 20 right there. Okay. Now, this is a constant. This x bar is constant. It's just we don't know what the constant is. And what can we do with constants and integrals? Pull them out. So this is x bar times the integral from 0 to 2, 2 plus 6x dx minus 20 equals 0 is what we sort of reduce this to. Yeah. This is a number. This is 2x plus 3x squared from 0 to 2, which looks to me like 14. No, 16. 16? 2 times 2 plus 3 times 4, 16. Okay, so what this all works down to is 16 x bar minus 20 equals 0. That's something we can solve. Right? X bar is 20 over 16, which is 5 over 4. Okay. So it looks really complicated and scary, but when you sort of separate out the two pieces, you realize, oh, these are all just pretty simple integrals. And that means that the balance point on that rod up there is exactly at the 1.25 mark, which makes sense because it gets heavier towards the right. So it should be, that doesn't look like 1.25. 1.25. So that's the place you would put your finger to balance this down. Okay, sorry if that was a little fast, but I wanted to get the formula is the hard part. The computation is actually not that bad once you write it down. Okay, let's call it a day. And there's homework for Friday. It's got a little bit, it's definitely got some point mass problems. You might have a one-dimensional center mass problem. I can't remember, like one of these kind of problems. But we're going to look at like 2D center of mass and 3D center of mass, and those I'll probably assign for next week. I'll check the homework to make sure I didn't give you problems that I don't expect to be able to do yet.
Thank you.
Thanks, everyone. Sorry to rush at the end.
I saw the same. Goodbye. Have a good
Yeah.
day.
Oh, thanks. You too.
Is this assumed constant?
Assume constant. That's what that says. Yeah. Sorry.
No.